All right, welcome to Finite Mathematics. We are going to start the course out by talking about systems of equations and matrices. So systems of linear equations is something you've almost certainly learned about before in a previous algebra class, most likely. A system of equations is just a set of two or more equations, and what we're trying to do is solve that system to find the variables that satisfy every equation in the system. So the example we have here is x minus 2y equals 1 and 2x minus y equals 5. So we're looking for a single xy value that we could plug into both of those and have both be true statements. So there's a number of ways in which we can solve these. One way is graphically. So if we have a graphing calculator, we could solve it. So these two lines cross at the point 3, 1. And that's what the solution to a system of linear equations is. It is just the literal intersection point of the two lines. And this is something that's going to be really important going forward. Because for all of this first unit, we're going to be dealing with things where we're trying to figure out where two lines intersect. And so that is what we're looking for here. So, like I said, there's a number of different ways we can solve these. Probably one of the most common is elimination. It is a method that you've probably learned. So, for example, we could do something like multiply the first equation by negative 2. So that would give us negative 2x plus 4y equals negative 2. And then we could add that to the second equation. So 2x minus y equals 5. And so we'd add those together. Negative 2x plus 2x is 0. 4y minus y, that's 3y. And then 5 minus 2 is 3. And then we could divide both sides by 3 to give us y equals 1. We can then take that value and plug it back into either of our equations to solve for x. So we could plug in 2x minus our y value, which is 1, equals 5. So just taking this second equation here, we could have used the first equation if we had wanted to as well. All right, so 2x minus 1 equals 5. We'll add 1 to both sides. So that'll give us 2x equals 6. Divide both sides by 2. And we get x equals 3. So we have the solution 3, 1, which we write as an ordered pair. So x is 3, y is 1. And that's, of course, the exact same answer we got graphically. So no matter how we solve these systems of equations, we're always going to get the same answer. All right, now that is a method that you've probably seen before. So we went through that one kind of quickly. So let's go through one more method that you may not be as familiar with, although you may. Some algebra classes cover it this way. And it's what's called the Gauss-Jordan method. So Gauss-Jordan. And the Gauss-Jordan method is a method of reducing a matrix down so that we can just read the answer right from a matrix. But the first thing we need to do is we need to put this system into a matrix. So a matrix is just an array of numbers with brackets on both sides. And basically what we are doing is noticing that there are a number of similarities between these two equations. So in both of them, the x's come first. So the x in our matrix will be the first column. The y's then come second. And then we've got an equal sign, and then we have the constants. So the equal sign we write as a vertical line. And what we're going to write in this matrix are just the coefficients, at least to the left of the vertical line, the coefficients of our variables. So x in the first equation is really a 1x, and then the y in the second equation, negative y is really negative 1y. So our coefficients for the x's are 1 and 2, and then the coefficients for the y's are negative 2 and negative 1. And then our constants are 1 and 5. So we have this matrix 1, negative 2, 1, 2, negative 1, 5. We call this matrix an augmented matrix. The right-hand side, is the augmented part. Augmented just means added on to. So we take the coefficient matrix, which is the left side, and we augment or add on the right side, the coefficients. So once we have the matrix in this form, we can use what are called row operations to solve the matrix. And really, this is just kind of a systematic way of doing the elimination thing that we just saw. So, for example, our first row operation would be we do negative 2 row 1 plus row 2, and that's going to be our new row 2. So we write that as negative 2r1 plus r2, and then we draw an arrow to the new r2. All right, so negative 2 row 1, that would be negative 2, positive 4, and then negative 2. And then we're going to add that to row 2. So 2, negative 1, and 5. All right, when we add those together, we're going to get 0, 3, and 3. And so that's our new row 2. So we'll rewrite our matrix. 1, negative 2, 1, 0, 3, 3. All right, our next row operation, we're going to multiply the second row by 1/3. So we'll write that as 1/3 R2 becomes the new R2. All right, and then we'll just rewrite our matrix after we do that. So we got 1, negative 2, 1, and then we're going to multiply all of row 2 by 1/3. So that gives us 0, 1, and 1. All right. So you may notice some similarities between those two steps and what we did in our elimination process. So the elimination process, let's get back to that real quick. We multiplied the first row by negative 2, or the first equation by negative 2, and added it to the second equation. And then we divided both sides by 3. It's basically exactly what we did here. We multiplied the first row by negative 2, added to the second row. And then instead of dividing by 3, we multiplied by 1/3. But same basic steps. So now we'll have one more step, and that's going to be 2 row 2 plus row 1. It's going to give us the new row 1. All right, so 2 row 2, that's 0, 2, and 2. And then plus row 1, so that's 1, negative 2, 1. Add those together, we'll get 1, 0, and 3. So our final matrix is 1, 0, 3. That was our new row 1. And then our previous row 2, 0, 1, 1. All right, and now we are finished with the Gauss-Jordan process. This matrix is in what's called reduced row echelon form. And so it is a reduced form of the matrix, where it has been reduced or simplified as much as we can. The reason why we want to get it into this form is because, so we still have our first column are our x's, second column are our y's. So if we were to take this and write those rows as equations, so we started off up here with equations, and we put it into a matrix. Now we're going to go in the reverse order. So we're going to take the matrix and write it as an equation. So that first equation, that's 1x plus 0y, which is just 0, equals 3. So 1x plus 0y equals 3, or just x equals 3. And then the second row, 0x plus 1y equals 1, that's just y equals 1. And so again, we end up with the solution x equals 3, y equals 1, or the coordinates 3, 1. So that is the Gauss-Jordan process. Elimination works just fine with 2 equation systems. But once you get to 3 equation systems, 4 equation systems, the kind of systematic method of the Gauss-Jordan method works really, really well. Now, what we're going to do in this class is we're actually going to let the calculator do this process for us. This class is really more about applying algebra. So this process is an algebra technique. So we don't spend as much time in this class talking about algebra techniques. We use them to solve application problems. So this whole process we can actually have our calculator do for us. So we'll look at that here in just a second. Before we do that, notice this right here, reduced row echelon form. The first letters of each of those words are R, R, E, F. And that is the function we are going to use in the calculator to solve this system. So let's go back to our original system. There we go. There's our original system. So we want to use the calculator to solve this system for us. All right, so we're going to put it into a matrix just like we did last time. So that's 1, -2, 1, 2, -1, 5. And we're going to put that into our calculator. So the way we're going to do that, we are going to press second and then matrix. We're going to go right twice to edit. We're going to press enter. Matrix A is going to be a 2 by 3 matrix. So it has 2 rows. 2 by 3. 2 by 3. So it has 2 rows and 3 columns. And then we just enter the elements one at a time. Press enter in between. So 1, -2. Do be careful on your calculator all semester. You'll notice we have both a negative button and a minus button. And the calculator is really picky about those two. If you just want to type a negative number, you use the negative button. If you want to subtract numbers, you use the subtraction button. It's really kind of confusing that there are 2 different buttons, but anyway, you'll get an error in your calculator if you use the wrong one. All right, so we have 1, -2, and then 1, and then 2, -1, and 5. All right, so now we have that matrix in our calculator. We'll do second and then quit. All right, and then we will go back to the matrix menu. So second matrix. We're going to go right 1 to math, and then we're going to go up to RREF, which again stands for reduced row echelon form. So this function does the Gauss-Jordan process to get it into reduced row echelon form. So the calculator function is named after the form that it gets it into rather than the process that is used to get there. So anyway, we'll select that, and then we're just going to select matrix A. So second matrix. We'll select matrix A and then press enter. And we get 1, 0, 3, 0, 1, 1. Same thing we got last time. So 1, 0, 3, 0, 1, 1. In the calculator, it doesn't have the vertical line separating the coefficients on the left from the constants on the right, but that's okay. We know that's where that goes. All right, so again, if we write those out as equations, which I would really recommend doing, especially when you're just getting started with this. A lot of people like to just look at the matrix and jump right to the answer. That's going to be dangerous here in a little bit. You'll see why. But anyway, always write it out. So this is x equals 3 and y equals 1. Those are our two equations there. And so that is the solution to our system. All right, let's look at a couple other systems, because this was one example of a system where our lines meet at a single point. So that is one possibility, but there's two other possibilities for a two-equation system of equations. So let's look at another example. All right, so now we've got negative x plus 2y equals 3. And 2x minus 4y equals negative 6. So we're going to use the Gauss-Jordan process again. We're going to use our calculator to do the Gauss-Jordan process for us. So we just want to put this into a matrix. So again, we're just looking for the coefficients. So the coefficients of the x's are negative 1 and 2. Coefficients of the y's are 2 and negative 4. We'll draw our vertical line, and then the constants are 3 and negative 6. So we've got the matrix negative 1, 2, 3, 2, negative 4, negative 6. All right, so now we're going to do the exact same thing in our calculator. So we're going to go second matrix, over to edit. And we can just edit this same matrix, matrix A, or you can put it in as a different matrix. Doesn't really matter. It's still a 2 by 3 matrix, has 2 rows and 3 columns. So we'll type it in, negative 1, 2, and 3. And then 2, negative 4, and negative 6. All right, so we'll then quit out of there. So you have to do this every time. You always have to quit out of this. Not sure why that's how they designed it, but anyway, second quit. We have to get back to this screen before we can go select the RREF function. All right, so then we'll select the RREF function. So second matrix, right one to math, and then up to RREF. Then we're going to select matrix A, so second matrix, select matrix A, and then press enter. All right, so what we get is 1, negative 2, negative 3, 0, 0, 0. All right, so 1, negative 2, negative 3, 0, 0, 0. All right, so this one looks a little different than last time, but the setup is the same. So first column are the coefficients of our x's. Second column, coefficients of our y's. Got our vertical line, and then our constants. All right. So again, we always want to write these out. This is where if you jump straight to trying to get the answer without writing out your equations, it's really easy to make a mistake. So let's write these out as equations. So first equation, that is x minus 2y equals negative 3. And then the second equation is 0x plus 0y equals 0, which is just 0 equals 0. It's not super helpful. It's true. 0 does equal 0, but it doesn't really give us any information that is helpful for this system. So what this tells us, because we have two variables and really only one equation, we have two equations, but we have only one unique equation. And anytime we have more variables than we have unique equations, we have infinitely many solutions. So this has infinite solutions. So our first type of solution was one solution where the two lines cross at a single point. This one is infinite solutions. And the way we're going to write our answer for this is by finding what's called the general solution. So the general solution is we're going to solve for our variable in terms of another variable. So for this equation that we've got, x minus 2y equals negative 3, we're going to add 2y to both sides and get x equals 2y minus 3, or negative 3 plus 2y, doesn't really matter. So that's our x-coordinate. So when we write our coordinates, it's going to be 2y minus 3, that's our x, and then y is our y. So that is our general solution. And we could plug in any value of y that we want, and we can get a new solution. So if I plug in 1 for y, and that's 2 times 1 minus 3, that's negative 1, and then plug in 1 for y, that gives us 1. So negative 1, 1 is one solution to this problem. If I plugged in 2 for y, that would be 2 times 2 minus 3. So 4 minus 3, that's 1. So 1 and 2, that is another solution to this system of equations. So there are infinitely many of those solutions to this system of equations. The y in this we call the parameter. So it is the thing we write the other variables in terms of. You'll also see systems with 3 equations, and in those, usually, actually always for what you'll see here, z is going to be your parameter. So you'd have all of your variables, x, y, and z, written in terms of z. So the only difference between this and a 3x3 system with 3 equations and 3 variables is you would solve, just like we solved for x here, and got x equals 2y minus 3, you would do that for both x and y. So not too different. All right, so what does this look like graphically? Why does this happen? The reason why this happens is those 2 equations are actually the exact same equation. So to create this example, I wrote the first equation, negative x plus 2y equals 3, and then I multiplied it by negative 2 to get the second equation, 2x minus 4y equals negative 6. So they're the exact same equation. They look different, but they're the exact same. And so that's why there's infinitely many solutions, because everything that's a solution to one has to be a solution to the other because they're the exact same line. So, all right, so we have one solution, we have infinite solutions. Let's look at one more type. All right, for our next example, we're going to take the system we just looked at, negative x plus 2y equals 3, 2x minus 4y equals negative 6, and we're going to change just that negative 6 there at the end to a 7. So we'll keep everything else the same, but this will be our new system. All right, so same thing as before. We're going to write this as an augmented matrix. So the coefficients of the x's, negative 1 and 2. Coefficients of the y's, 2 and negative 4. And then the constants, 3 and 7. So again, all we changed was that 7. So when we go into our calculator, we can go to second matrix, over to edit, and then we can just go down to that very last element and change that to a 7. Okay, all done. All right, so we want to quit out of there, go back to second matrix, write 1 to math, up to RREF, and then we'll select matrix A. All right, so we get 1, negative 2, 0, 0, 0, 1. So 1, negative 2, 0, 0, 0, 1. All right. So let's go ahead and write these out as equations. All right, so again, first column x, second column y. So we have 1x minus 2y equals 0. All right, so far so good. Second row, 0x plus 0y equals 1. So that's 0, equals 1. Well, we know that's not true. 0 does not equal 1. It doesn't matter what x and y are. We could put any values of x and y in, and it's still never, 0 is never going to equal 1. So this type of system has no solution. There is no value of x and y that can make both of those systems. There's no one solution that works for both of those systems. So what does this look like graphically? Well, it looks like this, 2 parallel lines. So what happened when I changed that -6 to a 7, I kept the left-hand side, which means I kept the slope of the line the same, but I changed the y-intercept. And so if you have 2 lines, both with the same slope and with different y-intercepts, then they will just run alongside of each other forever and they will never intersect. So these 2 lines have no solution because they will never cross. So those are our 3 different types of solutions: one solution, infinitely many solutions, and no solutions. So on any problems that you're working on, just be thinking about, okay, what do those 3 look like? So just to kind of recap, one solution, you'll end up for a value for x and a value for y. Infinitely many solutions, let's see, that was right here. Infinitely many solutions, you'll often end up with a row of zeros, but not always. The real way we can tell infinitely many solutions is if we have more variables than we have unique equations. Here we had just the one unique equation. Again, 0 equals 0 didn't really tell us anything. We had one unique equation, but 2 variables. So that means it had to be infinitely many solutions. Yeah. And then no solutions were, we had just this one equation, but then we also had a false statement, 0 equals 1. So we have any sort of false statement, that is going to be no solution. All right, so now that we've looked at the 3 different types of solutions, let's look at a word problem. All right, so, I will often choose word problems that are straight from your homework. While you're watching these videos, I strongly recommend taking notes, like you're with me in a classroom, because a lot of times I choose questions like this one, which are straight from the homework. So this question is in your homework, so I would write it down while you're working through it, so that way when you get to the homework question, you'll know how to work it. All right, so we have a company called U-Drive, and they plan to spend $7 million on 200 new vehicles. They're going to buy some vans, which cost $35,000 each, some small trucks, which cost $30,000 each, and some large trucks, which cost $50,000 each. They also want twice as many vans as small trucks. So we want to know how many of each type of vehicle should they purchase. All right. So what we want to do anytime we have a problem like this, the very first thing we want to do is to write out our variables. This is the step that most students skip, and it is the key to being able to work word problems. So I promise you it will make your life much, much easier if you do this. It's going to seem like a waste of time, I know, but it really, really will help. So writing out our variables, we need to know what is it that we are trying to solve for. The unknowns, those are our variables. So the nice thing is those are almost always in the question part of the problem. How many of each type of vehicle should they purchase? So let's let x equal the number of vans. So that's one type of vehicle. Let's let y equal the number of small trucks. And then let's let z equal the number of large trucks. All right. So now we've got our variables written out. And notice we were pretty specific. We included the units, number of vans. We don't want to just write something like x equals vans, because that doesn't tell us what we're solving about, for. Is it how many people can fit in the van? Is it how much the van weighs? Is it how much it costs? Is it its gas mileage? We need to know what we're referring to. So number of vans is our x. So that's pretty important. All right. So now that we know our variables, we want to start writing our equations. But the way we want to start writing our equations is with the constants. So those are the numbers that go on the right-hand side of the equation. So we got something x plus something y plus something z on the left-hand side. But the constants on the right-hand side are where we want to start. And the reason why we want to start there is because those will tell us what the units are for the equation. And that's also really important. All right. So our totals here, our constants, we have two of them, 7 million and 200. So 200, let's start with that one. So that's 200 vehicles. So we're going to start off with equals 200 vehicles. Okay, so we're going to write our units because it's important. So if we have number of vehicles on the right-hand side of our equation, then that means on the left-hand side of our equation also needs to be number of vehicles. In this case, the 200 new vehicles is made up of vans, small trucks, and large trucks. So the number of vans plus the number of small trucks plus the number of large trucks needs to equal the total number of vehicles, 200. Well, we wrote out our variables earlier, and we know that each of those variables is the number of those vehicles. So the number of vans plus the number of small trucks plus the number of large trucks, that's just x plus y plus z, and that equals 200. Our other total, 7 million, so we'll write out equals $7 million. So our units there, dollars. All right, so we have dollars on the right, which means we need dollars on the left. So the total spent is going to be the price of each vehicle times how many of those vehicles we're going to purchase. So vans are $35,000. So that's $35,000 times the number of vans that are being purchased, which is X. The small trucks are $30,000. So we're going to add that to $30,000 times the number of $30,000 small trucks we're going to purchase, Y. And then we'll add that to $50,000 per large truck times the number of large trucks that are being purchased, Z. So 35,000X plus 30,000Y plus 50,000Z equals $7 million. All right. So we've used our two totals, our two constants, 207 million, but we have three variables here. So I mentioned earlier, if we have more variables than we have unique equations, then we're going to have infinitely many solutions. So if we tried to solve this right from here with two equations and three variables, we're going to get infinitely many solutions. We won't be able to find an exact solution. But there's one more piece of information we haven't used yet. They want twice as many vans as small trucks. All right, so we need to use that to create our third equation. So to do that, let's first think about what would it look like if we wanted the same number of vans as small trucks. Well, in mathematics, if we want to say one variable is the same as another, then we would say they are equal. So vans and small trucks, that's x and y. So if they were the same, that would be x equals y. Okay, so that would be our equation if it said we want the same number of vans as small trucks. So they want twice as many vans as small trucks. So what I usually see people do here is this. Well, we want twice as many vans, so that's 2x equals y. Now, we can figure out why that's not going to work by just plugging a variable in. So let's say we wanted 10 vans. Well, the problem says they want twice as many vans as small trucks. So that would mean there would be 5 small trucks. So if there are 5 small trucks, that should be 10 vans. All right, so let's see if that works. So that would be 2 times 10 equals 5. Well, that's not right. That's 20 equals 5. We can tell that is not correct. So why does this not work? It seems like it would. Twice as many vans as small trucks. Well, the reason why is because this equation, 2x equals y, when we read an equation, we start with the variable if it's by itself. So what this says is y equals 2x, or the number of small trucks is double the number of vans, which is actually the opposite of what we wanted. So what we really want here is x equals 2y. And what this says is the number of vans equals double the number of small trucks. And that is exactly what we want. So now this isn't in the right form to put into a matrix, because to put it into the matrix, we need everything the same as the other 2 equations. And the other 2 equations are x, then y, then z, then the constant. So to get this one in the right form, we're going to subtract 2y from both sides. So we'll have x minus 2y, and then if we subtract 2y from 2y on the right-hand side, we just get 0. So x minus 2y equals 0. Now, when you're working these types of problems in your homework, don't try to just jump right to this. I see people try to do that, and it does not tend to end up working well. They're not sure where to put the negative sign, and it's just really confusing. I don't even try to do that. So start here. Start with trying to relate your 2 variables. Then you can subtract one of them over to get it into the right format. All right. So now what we want to do is we want to put this into a matrix. All right. So our matrix, so we'll kind of have to jump back and forth here. Our system of equations, x plus y plus z equals 200. So that's going to be 1, 1, 1, 200. Our second equation, 35,000x plus 30,000y plus 50,000z equals 7 million. All right, so that's 35,000, 30,000, 50,000, and 7 million. All right, and then our last equation, x minus 2y equals 0. There's no z in that equation, so we'll just have a 0 as the coefficient for the z. So we have 1x minus 2y, 1x minus 2y, no z, so that's 0, and it equaled 0. All right, so this is our system, so we're going to type that into our calculator. Move this over a little bit. All right, so second matrix, over to math, up to RREF. Whoops. We need to put our matrix in. Almost forgot. All right, so let's go second matrix, over to edit. That's what we want to do first. So this matrix is a 3 by 4 matrix. So we need to put in new dimensions. All right, so matrix is 1, 1, 1, 200. And then 35,000, 30,000, 50,000, and 7 million. All right, last row, 1, -2, 0, and 0. All right, now we've got all of that in there. All right, so now second matrix, over to math, up to RREF, and then we'll select matrix A. So second matrix, select matrix A, and then press enter. All right, so what we get is 1, 0, 0, 120, 0, 1, 0, 60, 0, 0, 1, 20. All right, so let's write that down. Let's see, 120, 60, and 20. All right, so 1, 0, 0, 120, 0, 1, 0, 60, and 0, 0, 1, 20. All right, so if we write that out as a system of equations, that's going to be x, which is the number of vans, equals 120. Y, which is the number of small trucks, equals 60. We can already see that relationship worked out. The number of vans is double the number of small trucks. So that worked out great. And then z equals 20. So the good thing about these types of problems is that we can double check our answers. So did we buy 200 vehicles? Well, 120 plus 60 plus 20, that's 200. We can see that the number of vans is double the number of small trucks, 60 and 120. And if we add up how much was spent, so $35,000 for each of the 120 vans, so 35,000 times 120, plus 30,000 times the 60 small trucks, plus 50,000 times the 20 large trucks, we would, in fact, get $7 million. So we could double check that we got all of our answers right. And I do recommend doing that on these problems. All right, so that's how we can work a word problem with systems of equations. So again, to recap, what we want to do to solve these is we first want to write out the variables. Always do that step. I know it's really tempting to skip over it. You're going to want to just write your x's and y's and z's and try to come up with equations. That is where I see people make the most mistakes. You need to know what your variables are. Second step, know what your constants are, your totals. We want to start our equations there, then do the left-hand side. I know that's not how we're used to writing. We're used to writing starting on the left and working our way right. But it makes it much, much easier if you start with the right-hand side so you know what the units are. Here it was vehicles, here it was dollars. One of the questions that I see people make the most mistakes on, there's a question you'll see in the homework about car frames and truck frames being manufactured by a company. And very, very frequently, what I see people do is they will add two numbers together and have it equal another number. The first number will be the number of car frames, and add that to the number of truck frames and have that equal a number of car frames. That just doesn't make any sense. You can't take some car frames, put it together with some truck frames, and then get only car frames out. Doesn't make any sense. So you could add car frames to more car frames to equal car frames, but you can't add two things of two different types of variables and have it equal just one of them. So always make sure everything is the same all the way across every equation. So dollars, 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 and dollars, for example. All right, once you have your equations written out, put it into the matrix, use RREF, and solve. All right, so that is systems of equations. So in this video, we're talking about systems of equations and matrices. So let's talk about some matrix operations. So matrices, we can do normal algebraic operations on matrices. So addition, subtraction, multiplication, all those sorts of things. We can't do division, actually, and we'll look at that in our next video. But let's look over the operations that we can do. So let's write out a matrix, matrix A. And that matrix is going to be 1, 2, 3, and 4. That matrix is a 2 by 2 matrix. That means it has 2 rows and 2 columns. So rows is always the first one. So that's 2 rows and 2 columns. So we always list it as rows by columns. All right, matrix B, we'll let that one be 0, 1, 2, -1. And it's also a 2 by 2 matrix. All right, let's start off by adding matrix A and matrix B. If I were to ask you to do this, even if you had never seen matrices before, you would probably guess how to do it correctly. It's pretty straightforward. So A is 1, 2, 3, and 4. B is 0, 1, 2, -1. So to add these together, we're just going to add the corresponding elements together. So we'll add the top left element, 1, plus the top right element, 0, to get 1. We'll add the top right element, 2, to the top right element, 1, to get the new top right element, 3, and so forth and so on. So 3 plus 2 gives us 5, and then 4 minus 1 gives us 3. So that is our new matrix, and that's A plus B. So pretty easy, pretty straightforward. Matrix subtraction works the exact same way. So we won't bother with going over subtraction because I'm sure you can do it. You can also do this process in the calculator as well. So you can just enter matrices in the calculator and add them together, and it'll give you the answer. All right, so let's define one more matrix, C. And let's let matrix C be 1, 0, 5, -2, 1, -1. All right, so now let's add matrix A plus matrix C. All right, so A was 1, 2, 3, and 4. C is 1, 0, 5, -2, 1, -1. All right, so when we try to add these together, we can add the top left element plus the top left element, get 2. The next two elements, 2 and 0, is 2, not 0. 3 and -2, that's 1. 4 plus 1, that's 5. But then what do we do about the elements in C that we have that don't have corresponding elements in A? Do we just assume A's are zeros? Or the answer is we actually just can't do this. We cannot add two matrices that are not the same size. To be able to add matrices, they must be the exact same dimensions for us to be able to add them. They have to have all of the same corresponding elements. So we could add a 2 by 2 matrix to a 2 by 2 matrix. We did that just a minute ago. We could add a 2 by 3 matrix to a 2 by 3 matrix. That would be fine because we would have corresponding elements. Whatever the size is, as long as our other matrix is the same size, we can add them together. All right, so that's addition. All right, now let's look at multiplication. So there's two different types of matrix multiplication. The first type is called scalar multiplication. And scalar multiplication is when we have something like 2a. So we're multiplying a matrix times a constant. So when we're doing that, a was 1, 2, 3, 4. So if we multiply matrix A by 2, we really just multiply every element by 2. We're kind of distributing that 2 times everything in that matrix. So we'd get 2, 4, 6, and 8. So that's scalar multiplication. We can just multiply a matrix times a constant and get our answer. So pretty straightforward. You can do this in the calculator as well, although it's not terribly difficult to do by hand. But that's scalar multiplication. All right, now let's look at matrix multiplication. So matrix multiplication is when we're multiplying two matrices together, like A times B. So A was 1, 2, 3, 4. and B was 0, 1, 2, negative 1. All right, now you can do this process in your calculator. I'm going to show you how it works, and you'll see why I'm showing it to you here in just a minute. So the way we multiply matrices is we multiply the row of one matrix, the matrix on the left, times the column of the matrix on the right. It's kind of confusing. So we'll multiply the first row of A times the first column of B. So when we multiply the first elements of each. So that's 1 times 0. First element of A's row times the first element of B's column, plus the second elements multiplied together. So the second element of A's row times the second element of B's column, 2. All right, so we multiply first row times first column. All right, then we'll do the first row of A times the second column of B. So that's 1 times 1 plus 2 times negative 1. All right, so now we'll multiply the second row of A times both columns of B. So second row of A, 3 and 4, times first column of B, 0 and 2. So that's 3 times 0 plus 4 times 2. All right, and then finally we'll multiply the second row of A times the second row of B. So that's 3 times 1 plus 4 times negative 1. All right, so when we simplify all of that, so the top left element, 1 times 0 plus 2 times 2, that's 4. The top right element, we have 1 times 1 plus 2 times negative 1. So that's 1 plus a negative 2, so that's negative 1. We then have the bottom left element, 3 times 0 plus 4 times 2. That's 0 plus 8, so 8. And then the bottom right element, 3 times 1 plus 4 times negative 1. So that's 3 plus a negative 4, that's negative 1. So A times B is 4, negative 1, 8, negative 1. All right, so what did we do here? Well, we multiplied the rows of A times the columns of B. So to do that, when we multiplied each, we needed the same number of elements in each of those things, meaning we needed the same number of elements in A's row as we needed elements in B's columns. So when we multiply matrices, A was a 2 by 2 matrix, B was a 2 by 2 matrix. To be able to multiply the matrices, the number of columns of A, that's the number of elements in each row, 2, needs to match the number of rows, or the number of elements in each column of B. So to be able to multiply two matrices, these inner dimensions need to match. So we can multiply matrices of lots of different sizes, but the inner dimensions need to match. So for example, we could have multiplied matrix A times matrix C, for example. So matrix A, so A times C. So A was 1, 2, 3, and 4. C was 1, 0, 5, negative 2, 1, negative 1. And we can multiply those together because when we multiply the row of A times a column of C, there's two elements in both of those things. So A is a 2 by 2 matrix. C is a 2 by 3 matrix. The inner dimensions match. So we can multiply them. However, if we tried to multiply C times A, so 1, 2, 3, and 4. Then we'd be multiplying the rows of C, there's 3 elements in those, times the columns of A. There's 2 elements in those. So this we can't do. We can multiply A times C, but we cannot multiply C times A. And that brings us to a really important part about multiplying matrices, and that is when we multiply two matrices together, A times C, we don't get the same thing if we multiply them in the reverse order. Even if we can multiply them together, we don't get the same numbers, and sometimes, like here, we can't even multiply them. So this is one big difference between multiplication with real numbers, which is the multiplication you're used to, and matrix multiplication. We cannot swap the order of two matrices because that changes the answer. So that's going to be important when we solve matrix equations, which we will do in our next video. This is also the general rule. So when we switch the order of any two given matrices, the general rule is they will not equal one another. However, there are a couple exceptions to that rule, and we will talk about those exceptions in the next video. All right, that's it for this video. I'll see you next time.